Okay, not really sure how to start this off, never done this before, but welcome to the first episode of SpaceTyme. I'm sitting here today with Dr. Alexander Schenkel, who is my quantum field theory professor. First of all, I'd like to thank you very much for agreeing to be on the first episode. I know you're quite busy, so I appreciate your time. Why don't we start off by you kind of introducing yourself to our audience and giving us a bit about your story, how you got to this position, what ignited your passion for physics and mathematical physics in particular, and kind of your current area of research at the moment.
Okay, so yeah, I'm Alex Schenkel. I'm originally from Germany. I studied in Würzburg and I did my PhD there, and then I went on to do a few postdocs, Edinburgh and Germany, and then I ended up in 2016 here at Nottingham as an assistant professor in mathematics. So my area of research is in general linked to the intersection between quantum field theory and pure mathematics. So I'm in particular interested in giving mathematical sense to quantum field theory. Mm-hmm. I find that interesting because that is kind of, it touches both of my interests in physics and in mathematics, and it's a nice combination thereof.
Yeah, amazing. So in particular, what are you looking at the moment?
Yeah, at the moment I'm trying to kind of compare different axiomatizations for quantum field theory, because as a mathematician you want to give axioms to whatever you want to describe. You study, for example, linear algebra. The first thing people are doing is they define you what is a vector space, and then you prove some results about vector spaces. Yeah. Now in quantum field theory it's a bit different. People introduce that to you in lectures typically in the following way. They start with some examples, give you some intuition, and then move on from there. So when you want to do quantum field theory as a topic in mathematics, you should establish axioms for that. The problem is not that there are no axioms for quantum field theory, but there are too many axiomatic systems. There are at least 3 of them at the moment which are competing against each other. So one would like to understand if there are ways how to show that these axiomatic systems are compatible. Yeah. And this is a topic I'm currently working on.
So when you say competing against each other, does that mean they kind of contradict each other at the same time?
No, that is the question. I mean, they're competing against each other because they were kind of developed from different points of views, but they should describe essentially the same concept, namely a quantum field. Okay. But they describe it using different mathematical tools. Right. So the question is, can you link those different descriptions and make sense of them being the same or being compatible? So this is what I mean by comparing. And
so would you say it's kind of similar to, or analogous to, the link between general relativity and quantum mechanics? You know, 2 different ways of describing things, but trying to link them together in a sense.
So general relativity and quantum mechanics, how they are originally introduced, they should describe different concepts. General relativity should describe space-time, and quantum mechanics should describe particles or matter. Mm-hmm. So there it's of course also important to make them compatible. This is then what leads to, for example, quantum gravity and related subjects. Yeah. But for quantum field theory and the different axiomatizations, it's more basic, the problem. So you have the same concept, the quantum field theory, but you describe it using a different language. Right. And so these different languages should be somehow compatible, and people are currently thinking about comparing and proving precise results about their compatibility.
Okay, awesome. And is that something a lot of physicists nowadays are studying, or is it kind of a bit of a rare topic?
This is mostly done in mathematics at the moment. So physicists are not so much caring about the foundations of subjects. They are typically more interested in developing a subject well enough to then explore for new physics. Yeah? Yeah. So this is what kind of is the difference in the mind of a physicist and a mathematician. Mathematicians want to have precision and rigor, and physicists want to explore new and interesting directions.
Right. So would you say your topic is something that a lot of mathematicians are looking at?
Especially mathematicians in that intersection of pure math and quantum field theory, yes. So there is quite some activity at the moment in UK, in Germany, in US. So it's kind of worldwide. People are studying these kind of things.
Going back to like how you kind of got here, what was it like for you as a student? Learning mathematics, learning physics, and what was the journey like for you to get from point A to point B of being here at this prestige position you are right now?
So as a student, yeah, I have to say I started studying physics. So my original studies was in physics, and I was not really sure which direction to go, because you start in year one and you have no idea what is interesting and what is kind of good for you to do. So I was not even sure if I should do theoretical physics or more kind of applied kind of things.
Yeah.
So while studying, you develop a taste, and I would say starting year 2 or 3, it was kind of clear to me that the theoretical directions is what I'm interested in.
Yeah.
So I moved on in that direction, and then of course the more you look into foundations, the more kind of you turn into mathematics. So after studying physics, then I moved on to mathematics positions.
Yeah, I imagine it's quite difficult as well. I imagine it's quite difficult.
Yeah, it's not easy to change. I mean, I changed after PhD, and my PhD was still in theoretical physics. So it's not easy, but one can get that done if one puts energy in that.
Yeah.
So then I made it to get a postdoc position in Wuppertal, that is somewhere in the north of Germany, and then from there I got a fellowship to go to Edinburgh. And this was a beautiful time. So Edinburgh is a very nice city.
Yeah.
Then after Edinburgh, quick trip to Germany, and then here to Nottingham. So then the way how to, during these postdoc years, one has to establish oneself. You have to find your own kind of topics. You have to make your own progress in your own projects, and then hope that other people see what you do. I think that is the way how to make the step from postdoc to permanent position.
What was it like for you trying to find a position that aligns with your kind of research interest?
Universities often hire individuals, so you don't have to find exactly a university aligned to your research interest, but there should be a group of people who you can sensibly talk to. So,
right.
So it's not like you have to find exactly the university doing exactly this kind of line of research.
Okay. Yeah.
So it's more important that you have a group of people with similar interests around, that you can get different points of views and good interactions.
Okay.
And that is in Nottingham nice. So we have here a bunch of people in mathematical physics with similar interests, a bunch of people in pure mathematics with similar interests. So we have interactions on a daily basis, I would say.
And do you interact a lot with, like, for example, other departments, like the engineering department? Do you see a lot of potential worldly impacts in the research you're doing currently?
Engineering, I'm not really interacting with engineering. Colleagues of mine do. It depends always on the kind of topic you're working on. So the topic I'm working on is not too close to engineering, I would say. So I like to talk to these people. Sometimes I meet them when I have to take, say, development courses at university. So everybody has to do these professional development courses. You see people from other departments, and it's nice to talk to them. But on a scientific level, I think it's too far away that we don't have common interests. But other colleagues of mine here, they interact and collaborate with engineering, for example. These are mostly the people doing stuff like numerics for PDEs and more applied subjects.
It's very interesting. So what do you see in the future of mathematical physics? Because I know it's quite a theoretical subject. But for example, quantum mechanics 100 years ago used to be very theoretical, and now we're at a point where we're kind of implementing those ideas into something physical like quantum computing.
Mm-hmm.
Do you see in the future your kind of area of research, or mathematical physics in general, becoming something that we can actually apply into technology that we see in our daily lives?
Yes, there's a lot of progress at the moment in this direction. So the kind of research I'm doing is linked to a topic called topology. So there's now a lot of impact of topology on more applied directions. So for example, topological insulators are new kinds of materials which are based on topological phenomena to give you new technological advances. So topological insulators and various other things, they are concepts which came out of mathematical developments over the last 20, 30 years.
Right.
So especially the specific types of quantum field theories called topological quantum field theories, they're very useful for modeling and understanding these materials. So I think the most direct impact on daily life mathematical physics, especially in the form of quantum field theory, will have is on these new types of materials which rely on topology.
Okay. Would you mind elaborating a bit on like the type of materials, how they would impact us?
So I'm not really an expert on that, but so So if I get the point right, when you build realistic devices, there's always a bit of problem about, you have some fluctuations in the construction, and then if the material is not built good enough, it will not work well enough.
Yeah.
So the construction process of devices, you have to be very careful to build them precisely.
Right.
The advantage of topology is that it's more fault tolerant in the way that the phenomenon which the material should do comes from topological aspects. So if you slightly deform it, so think about the donut and coffee mug kind of example, if you slightly deform it witithout tearing it, it will still have the same properties.
Right.
So and then it's kind of, from a practical point of view, easier to build these kind of materials because you don't have to worry so much about the precision in the construction process. So so you get devices which have properties which are stable under impurities, I would say. So this is maybe the best way how I can describe it.
No,
does it make sense?
Yeah, that actually does, to be fair. What else do I want to ask you? I want to say, so with mathematics, obviously using a lot of tools, for example, that may have been invented in the past by other mathematicians. I want to ask you, what's your opinion on the kind of debate of whether mathematics is invented or discovered?
Going into the philosophical direction. So is there any fundamental truth about mathematics, or is that something we just made up? So this is essentially your question. My tendency is towards that there is a bit of fundamental truth about it because it simply works so well. When you think about how well mathematics works, I mean, you describe nature, all sorts of nature. You describe physics, chemistry, biology, all those things you have mathematical explanations for that. So it's definitely a super universal tool which works extremely well.
Yeah.
And I think it reflects the real world accurately. You can reflect the real world accurately using mathematics. So it has something to do with reality. It's not something people just made up and to have fun.
Do you think it's sort of like a language? You know, there's a famous quote like mathematics is the language of the universe. Do you think it's just kind of our representation of the underlying logic beneath it that's fundamental? Yeah,
that is definitely the case, I would say. So how we precisely describe a mathematical concept is up to us, and it kind of is biased by how we think about the world, I would say. So it is a language mostly, but it's a language trying to scratch on some fundamental truth, I think.
What do you find most interesting about quantum field theory at the moment?
In which sense? So what it achieves, or what it...
Anything that comes to mind.
I think a general thing which I find interesting about quantum field theory is that that it has an extremely broad scope of applicability. So quantum field theory was originally born in high energy physics. People were interested in particle scattering and how to describe that and how to annihilate and create new particles, and this is what kind of gave rise to quantum field theory. Now, people realized that the same techniques, quantum field theoretic techniques, can be used also to describe statistical systems, or as I mentioned before, these new types of materials. So quantum field theory has various other applications, not only in high energy physics, but also in statistical physics, condensed matter physics, and all other directions. I've even seen some guys applying quantum field theoretic techniques to model something really applied. So they were interested in constructing turbines, so turbines, big turbines which rotate, and there of course you have to be careful again the errors in the production.
Yeah.
That when it goes wrong and the turbine flies off, it's not good for anybody. So how do you model these fluctuations on the turbine? They use quantum fields to model these fluctuations, and this they did not in an academic environment, but in a company. So and this worked super good. So they used then these fluctuations described through quantum fields to turn them into failure rates, and this modeled the problem extremely well. So it's some kind of tool. The idea of describing kind of a continuum field with some random fluctuation on that. This is kind of quite interesting and quite far-reaching, I think. And this is the underlying idea of quantum field theory. So this is, I think, what makes that subject interesting.
The kind of applicability of it, how you can apply it to pretty much anything.
You can apply it to pretty much anything, and then if you look at it from a mathematics perspective, it leads to interesting mathematics. So it's kind of good for everybody. You can do applications, you can do fundamental physics, and you can inspire new mathematics. So what else do you want? I think it's good for everybody.
Yeah. So you're saying it can be applied in kind of an engineering sense as well. Say for example, with like even something as random as SpaceX, for example, you know, with the future of humanity, we're trying to launch ourselves to other planets, you know, almost take over the galaxy in a sense, yeah. Do you think quantum field theory has very good applications to stuff like that as well?
I don't know exactly. I think it's more an engineering problem and all sorts of other problems which come in trying to shoot people away from Earth in rockets. So I think this is it's a different kind of problem.
So quantum field theory is at the moment kind of as far as we've got with theoretical physics, correct me if I'm wrong.
So they're more speculative directions. I mean, string theory, quantum gravity. So they're more speculative directions, but I would say quantum field theory is as far as you got in established physics. I mean, which is not speculative.
Yeah. And so, are there any? I mean, I'm sure there are certain gaps in quantum field theory. Would you mind elaborating on some of those?
So I think from a practical point of view, quantum field theory works well, but from a conceptual point of view, it does not work very well. So for example, this is linked to that issue that the mathematical foundations are not yet sorted. So this is, you probably heard about this Millennium Prize problem, Young-Mills Millennium Prize problem.
Yeah.
So it's a mathematical problem to define what is a Young-Mills theory. So Young-Mills theory is appearing in the standard model, describes weak force, strong force, so people know it and see it in nature. But to define and construct Young-Mills theory in some rigorous mathematical framework is not yet achieved. So it's one of the open problems, and it's an important one. I mean, you get $1 million when you solve that. So there are clearly open problems in that subject, especially when it is about to precisely say what you're talking about, establishing axioms, and importantly proving that the axiom systems you have Young-Mills and other realistic examples as examples. So these are hard problems,
right?
Which are open since, I don't know, 50 years.
What do you see in the future in terms of those problems? Do you see them getting solved anytime soon?
I don't know. These problems are so hard that you don't know. I mean, what people tried back then in the early days was to try to attack that problem directly. So they used heavy analytical technology to try to construct Young-Mills, using measure theory and all sorts of other stuff. They figured out, not relatively quickly, but they figured out eventually that this is impossible because the problem is way too hard. So these direct methods people were trying over the years, they stopped like for 2-dimensional, 3-dimensional quantum field theories, and we need a 4-dimensional Young-Mills theory, which is like the next level of complicatedness. So then it looks like the direct attack doesn't work. So people have to find kind of a backdoor to the problem, and that is, you can compare that to kind of conquering a castle. You can try to smash in the front door, but this rarely works. You have to find the back entrance and then solve the problem. So I think this is what people are trying to do nowadays. So they're not trying to attack the problem directly, but to explore the region and see where's the weak point where one can enter and make progress.
Right. And so, for example, in the past, certain problems would have been a lot easier to solve in the sense of you can address it with a direct attack in a sense. But as time has gone on, these problems have got a lot more complicated and they're a lot harder to solve. So because of that, do you think we're sort of reaching close to the limit of
how far we can go? Yeah, life definitely doesn't get easier, because typically the easy problems is what people solve first.
Yeah.
But yeah, the problems get harder, as you say, but the technology gets better. The techniques you have in order to attack problems gets better.
Yeah.
So this is again not something just in mathematical physics, but in various branches of mathematics. People develop new technology which allow you to prove things which were impossible before. So I think that is, it balances, yeah. So the problems get harder, but the techniques get better, and so there will be continuous progress.
Do you think they progress at the same rate?
I don't know. I don't know. Hard to say.
Hard to say.
I mean, the problem goes harder, the technology goes better, but which is deeper, I don't know.
Well, yeah, it's just because, for example, these problems have been struggling with for like 50 or so years, and still no one's come up with a good solution to date. So it does kind of make you think, are we reaching the limit, if you know what I mean? Do you think there is a physical limit, or like an actual limit to how much or how far we can go with mathematics?
In understanding mathematics or nature, or both? Probably both.
Probably both,
so,
yeah.
so mathematics, I mean, you can always go further, of course. It depends on how you define progress. I mean, you can always generalize stuff. You can always do something new on top of existing things. If that makes sense or not, it's a different discussion. But you can, in principle, push it further.
Yeah.
So for mathematics to develop in a healthy way, it needs kind of directions, inputs. So in which direction to develop. So physics often gives inputs for new mathematical problems, but also other kind of areas give inputs. For example, recently also computer science gives good inputs of how mathematics should develop by there are new kind of forms of logic which are used in computer science, which also inspire a lot of mathematical developments at the moment. So you need to develop mathematics, you either need a good problem inside of mathematics, a conjecture which you want to prove, to develop new methods which allow you to prove the conjecture, or you need input from outside to tell you in which direction to develop. And I think as long as there is progress in surrounding disciplines, physics and computer science and other kind of scientific disciplines which give input for the development of new mathematics, I think it will not stop.
Okay.
And also at a more practical level, I mean, the challenge is mathematics is not just about concepts, it's also about like applied solutions. A lot of people spend their career developing, say, good numerical methods to solve differential equations, and then they apply that in engineering or in other fields. So there, of course, with the technological advancements, you have more and more possibilities to get better and better tools to get numerics done, to get simulations done, to especially that applied mathematics in computing intersection, this also grows, and this doesn't and this also benefits from inputs from outside. Good problems in engineering, good problems in other sciences, which you then develop new mathematics from. So I think mathematics is so universal that it will not stop at any point. And also physics, I think, will not stop, because you will always find new and interesting things. You don't have to go to super high energies in order to see new interesting physics. So at the moment there's a lot of interesting physics in condensed matter, as I told you before, with these new types of materials.
Yeah.
So I think these things will not easily stop. People will always come up with something new which will be interesting and eventually hopefully useful.
So going back to quantum field theory in general, that's kind of a progression of quantum mechanics, right? In the sense of it combines it with special relativity.
Yeah.
And so is what we're struggling with at the moment trying to take that step further and combine it with general relativity?
Oh yeah, that is then leading to this quantum gravity problem. I mean, there are two ways how to combine quantum field theory with general relativity. So let me maybe elaborate on that. So you can now ask, when you start doing quantum field theory, people will tell you, okay, you start on a Minkowski space-time and then you do quantum field theory, quantum fields on it. You can now ask, okay, if I have another space-time, a curved one, de Sitter, or a black hole or whatnot, can I do quantum field theory also on such kind of curved space-times? And that is an established research direction. So that works pretty well. You keep the space-time classical and you put quantum fields on top of that. So that's pretty well developed. What is not so well developed, even though there have been a lot of attempts, is when you try to make space-time itself dynamical and quantum. So this is then the quantum gravity issue.
Yeah.
So yeah, they are combining quantum and general relativity. There's still a lot of open problems in this direction.
Could you tell us a bit about loop quantum gravity?
I'm definitely not an expert in that, but I can say what I know about it.
Yeah.
So loop quantum gravity is I would say a relatively direct approach to try to quantize the gravitational field.
Yeah.
So the gravitational field is a field, let's say a metric on space-time, and this metric field you now want to quantize using some sorts of quantization prescription. So you can do that naively. You can try to say, okay, I take the Minkowski metric, I perturb around it and do some standard quantum field theoretic approach. But this leads to issues because these quantum field theories coming from metric perturbations are not as well behaved as Yang-Mills theories, for a reason I might come back if you ask me later. Loop quantum gravity is a way to say, okay, we have to be careful how to quantize the gravitational field. So the metric itself is maybe not the best type of variable to describe the gravitational field. So what loop quantum gravity does is it describes gravity in terms of different variables. So these are called field binds, and have you heard about that, field binds?
I haven't, no.
So you can, field binds are in a way giving you orthonormal frames at each point. Yeah. So once you know an orthonormal frame and how it varies from point to point, it also encodes some kind of geometric information. So it's a different choice of variables, which seems to be more fundamental than the metric variables. So loop quantum gravity is change the variables to more suitable ones, and then try to produce quantizations in these new variables. And this works better than with metric variables, but I think the issue with loop quantum gravity is that you can do that, you can set it up, you can understand the theory to a certain extent, but how to get a semi-classical limit, how to get classical spacetime as a limit from loop quantum gravity is not very well understood.
Right.
Because you have to think about that. So general relativity itself at the classical level is a space-time, so it's something very big, and loop quantum gravity starts from nothing. I mean, the vacuum of loop quantum gravity is no space and time at all.
Yeah.
And then you start exciting bits and pieces of space-time into there. So these are like very, very tiny universes which are easy to be described in loop quantum gravity. And then you have to kind of take a lot of tiny pieces and try to build continuum space-time out of that, and that is super difficult and super involved. So it's the continuum limit, which I think people don't have very well under control.
All right, okay, that's very interesting. When it comes to black holes, how do you think your current area of research plays into the dynamics of black holes and how they work?
Not much. I'm
Not
not
much.
focusing very much on black holes. We have colleagues of mine are focusing a lot on black holes. So we have here a quite big gravity group, and they're doing gravitational waves coming from black holes, or numerical relativity for rotating black holes and colliding black holes and whatnot. So I think other people here in the department will be able to tell you much more about black holes than I.
That's fine. But do you think quantum field theory is like a big character, a big player in determining how the dynamics of the black holes?
Quantum field theory tells you something about black holes. So there's this phenomenon called Hawking radiation.
Yeah.
So black holes are kind of radiating off quantum particles. So that's a quantum effect which you can describe from using quantum field theoretic techniques on curved spacetimes. So quantum field theory tells you a bit about black holes. It gives you some insights that they are not like stable. They radiate off particles and eventually decay. So if you see that in reality, not really, because the real black holes are way too big. That so when you see how the temperature of this radiation changes with the size or the mass of the black hole, then for realistic black holes these effects are negligible. So the more massive the black hole, the lower the temperature. This is kind of the relationship. So you would need very tiny black holes to see them radiating off.
Yeah.
But I'm not aware of tiny black holes, and I don't want to have them here on Earth. Yeah. So quantum field theory tells you a bit about black holes, about their properties, but not in a realistic scenario where you have like an astrophysical black hole sitting at the center of your universe. This doesn't radiate much.
Okay.
So it's more a theoretical kind of insight you get.
Okay. If you had to pick, for example, another area of theoretical physics or mathematical physics that you'd be very interested in researching, what would that be?
Good question. I think I come back again to these topological materials. This is something which happened after I started my PhD. Yeah, so this is something relatively new, and over the years I got more and more kind of. I never worked on that subject, but I see more and more what other people do. I think this is a very interesting topic. So topology in materials. Yeah? So that is a quite interesting subject. So I would go in that kind of direction if I would be forced to do another direction.
But if you weren't forced, you'd probably stay on this kind of path that you're on right now.
Yeah. I mean, I like the subject I'm working in. It's a nice subject. It's this interplay between physical concepts and new mathematics, which kind of attracts, which I find attractive. And this you can have in quantum field theory, and this you can also have in topological insulators, in other directions.
So you mentioned you made that kind of switch after your PhD in terms of your thinking or your interests. What would you say to someone who's sort of almost been studying a certain topic for quite a while, number of years, and they're thinking of making a sort of switch? Because I know you can get very attached to the kind of topic that you're studying, especially if you've been studying it for quite a number of years. At what point do you think, okay, it's time to make a switch? What kind of factors go into making that decision?
Yeah, making a switch, human beings like to stay on their trajectory, so making switches is never easy, but sometimes it's sensible. I mean, when you see that you develop new interests, and when doing research, the most important thing is that you must be interested in that, because this is the kind of freedom you have in research, to do something you're genuinely interested in. If you want to do something for the sake of earning money, then you can also go to a company and they pay you better. So the most important thing about research and academic life is work on topics which you're really, really interested in. And if it turns out that your interests change over time, and this can happen, I mean, one starts studying or one starts doing PhD, one doesn't have a good overview of what's going on. Then over the years you meet more people at conferences, you see kind of other topics, and you see, it's interesting, and you get attracted to that. It's kind of good to continuously kind of maybe adapt a bit, because just staring narrow on your trajectories is not good. One has to adapt also to the other people, because science is a community effort. It's not like an individual plowing through and doing exactly what you want. When you are interested in kind of branching out a bit, do it. I think that is always something good to do.
Right.
And the way how to achieve that in practice is find someone who knows about the other subject and collaborate with them.
How do you pick a field in the first place? I know you said, choose something you're interested in, but for someone who's interested in also making an impact, having their name, get established, there are a lot of scientists whose work kind of never really goes noticed. They spend 40-50 years studying a subject and they never really help make any progress. So what would you say to someone who's trying to look for something that will actually get the name established?
Yeah, the problem is you cannot control that things from the beginning. So you work on a certain topic, and if that now will solve major problems and lead to major progress, you don't know at the beginning. So you have to kind of follow your intuition, or when you're young, maybe also supervisor's intuition, to work on promising directions and hope that they lead to good impact. And you can never control that stuff from the beginning. If you know the outcome before you start doing the work, then it's not research. I mean, you see what I mean?
Yeah.
Research has to be kind of, there must be a question, is that true or not? And so it's always a bit unpredictable what happens. So I think, especially for younger people, the question should be something like, how do I know in which directions to go when I do PhD, for example? Yeah? So that is the first kind of time when one has to specialize. So of course one can also specialize before. I mean, you can study mathematics, physics, mathematical physics, or whatever. So there are various directions, but I mean specialization within a certain field. So in your case, mathematical physics. The first time you really have to specialize is when choosing a PhD, or when thinking about in which directions to go in PhD. And I think there, go with your gut feeling. Talk to people, see what are the options, and say, this is something I would like to do. I now spent the next 3-4 years putting energy in that. If that is not exactly what at the end you like to do, there's always still the kind of possibility after PhD to slightly change direction. So you can always adapt to something new, and I've done that myself, so it's possible.
Right. You think it's possible to make a complete switch? You said you can kind of adapt slightly. Do you think it's possible to make a switch that's like 180 degrees after your PhD? Or
I don't know. I mean, complete switch. I think I will not become now a chemist, so this would be impossible.
Yeah.
But sometimes there are relatively big switches. I mean, I've seen people who went. Yeah, I've seen people who went from abstract homotopy theory to now data analysis or so. So there are sometimes concrete, very big switches happening.
Yeah.
Even late in their careers. So these people, they were like, I don't know, they were like in their 50s when they switched.
Oh, wow.
So yeah, it's always do what you kind of like. And I think, and when this requires a bit of switching, don't do it abruptly. Try to kind of test it out a bit if that new direction is something for you.
Yeah, test the waters a little bit.
You have to test it, because when you put your step completely out and you're out, then you never come back, you know. So you have to see to always, when trying to switch, keep one foot inside the old part and one foot inside the new part, and try to see how it goes.
There are a lot of key players, key scientists in the development of quantum mechanics and quantum field theory. If you could sit down, have a conversation, ask them any question, who would you sit down with and why?
Oh, good point. I think I would have enjoyed talking to Dyson. Yeah, Dyson did very important work, and he was also well mathematically educated. He has a background in mathematics, but then he kind of switched. Yeah, he switched from something in number theory, I think, to quantum field theory, and made good progress there. But he's of course well known historically, but I think he didn't get the kind of level of fame and level of how do you say, appreciation which he would have deserved. And I would have liked to talk to him to kind of see his thinking, because he realized also quite early. He wrote this nice paper called Missed Opportunities. So when he kind of talked about that the mathematician Dyson and the physicist Dyson didn't talk to each other somehow, and he would have enjoyed them interacting more with each other. So I would enjoy having a chat with him, and just to see how he ticks.
Yeah. And is there any questions in particular you'd ask him?
Why did the two Dysons not interact with each other? Yeah.
I'd like to ask you my final question, which is, what is the impact that you wish to kind of have on the world? What's kind of like an ideal future for you yourself and that you see for the planet? And how does your field, or just theoretical physics in general, play into that?
Ooh, that's a tough question. So what is the impact that I'd like to see? So of course, I mean, unrelated to my work, I would like to see the world not kind of going totally mental. I mean, that is the first kind of thing I would like to see, that people kind of start calming down again and then start behaving more like humans. How my work has impact on that, probably not much, but no, I would like to see, from a more work kind of perspective, I would like to see the Young-Mills problem solved in my lifetime. So yeah. I'm not claiming that I will solve it, probably not, but I would like to see it solved, and I do all the best I can do to and if that is solved, then this has, okay, I mean, the practical impact is probably not so high, but it is a big conceptual impact, because it tells you that what people are using to describe fundamental physics exists at a certain level of mathematical rigor, at a high level of mathematical rigor, and that is, I think, important, because it tells you that the tools people are using to describe nature are really proper tools, and that they are not kind of flawed in some sense.
Right, okay, that's amazing. Thank you very much. Yeah, this was my first time doing this.
And mine too.
And yours too, so there may have been, some times where I was thinking, oh, what do I say, what do I ask? It's fine. Same with you, you might have thought there were some points where you're like, oh, what do I say? But I think generally it went very well. I wouldn't worry about anything. And yeah, you were very interesting to talk to. We'd love to have some more conversations in the future. Sure. And yeah, look forward to seeing you in later lectures. And yeah, again, thank you very much for your time.
No worries. Thanks for the interview.
Thank you very much.